Hey folks, this is your second lesson in our nuclear chemistry unit, and in this lesson we're going to be talking about two particular types of nuclear reactions, fission and fusion. These are going to be a little bit different from the nuclear decay reactions that we talked about last time, although when we write out these reactions they're going to be very similar in terms of the conventions that we use. So our main goals for this lesson, first of all, talk about what fission and fusion are and how they are different. Second, practice writing those balanced nuclear reactions to describe those different types of reactions. And then and just talk a little bit about some of the effects of being exposed to radiation. Okay. So just to finish talking a little bit about nuclear decay. So previously, if you recall, we talked about alpha decay, beta decay, positron emission, gamma ray radiation, etc., etc. And one thing that we didn't mention before is that sometimes just going through one round of decay isn't enough to make an isotope stable. Now, if you recall, what we find is that our heavier elements tend to be very unstable, and so they decay and often will throw off part of themselves, and that helps them to be a little bit more stable, to have a better ratio of number of neutrons to overall atomic mass. But again, sometimes this isn't quite enough. So if, for example, we consider polonium-212, okay, we could have it undergo alpha decay and we would end up with lead-208. Now that's good, we've made our atom more stable, but sometimes that's not enough. Maybe even our lead-208 is not stable. So what we'll find sometimes is that that new product from our previous decay will undergo another instance of nuclear decay. So for example, in this case, we had our polonium-212, it decayed into lead-208, and then that lead-208 further decayed into mercury-202 before it became stable. Now this is an example where it only had to go through 2 rounds of decay before we reached a reasonably stable isotope. If we have something, for example, like uranium-238, which is very famously unstable, our decay series might, start off with alpha decay, and then take a couple rounds of beta decay, and then a couple rounds of alpha, a couple more of alpha, another alpha, a couple more beta, another alpha, another beta, another alpha, before we finally end up with something stable like lead-206. So what we find then is that these nuclear decay reactions may not emit a ton of energy in and of themselves, but sometimes we get this series going where we have lots and lots of reactions occurring one after the other. So that's all I have to tell you about decay for now. We'll move on to fusion at this point. Now, if you recall, hopefully from somewhere else in your science education, our sun is really just a star. Just like any of the stars that we see out in the sky, and those stars are pretty big. In fact, our sun, which is sort of a medium-sized star, is 333,000 times the mass of the Earth. And the Earth itself is pretty big, so when we get 333,000 times bigger than that, we're talking about something pretty darn big. So most of the mass of in the universe is held within stars. And stars are mostly hydrogen. They're mostly just protons kind of bouncing around doing their thing. So we've got lots and lots and lots of hydrogen out there. But of course, we need other elements, as hopefully you have figured out at this point. We need carbon, we need oxygen, we need nitrogen, we need all sorts of heavier elements than just hydrogen. So the question is, how is it that if our stars are all made up primarily of hydrogen, that we ended up with all these other atoms that came to be? And this is through the magic of fusion. So the idea behind fusion, if you think of fusing two things together, we're talking about taking two separate items and combining them together so that they are attached as one larger unit. Same idea in nuclear fusion. So what's happening in our sun and all the other stars right now is they're taking different hydrogen atoms and basically smashing them together, fusing them together. And as they do that, number one, they create heavier atoms, and number two, they release a bunch of energy in the form of heat and light, which is, why the sun gives us heat and light. It's because there's nuclear fusion happening, because it's taking all these hydrogen atoms and fusing them together to make these heavier elements. Okay. Now if we look way down the line, when a star runs out of hydrogen, it'll start to fuse together other things. So instead of fusing together two hydrogens, maybe it'll fuse together a helium and a hydrogen, or a helium and a lithium, or something like that. So we'll keep fusing together our elements over and over until we end up with heavier and heavier elements. Now eventually though we'll reach a point where we've kind of hit the limit in terms of what our star can fuse together. At that point it could go cold, or it could basically explode in this amazing nova or supernova, which is, number one, pretty darn exciting. But number two, when a star dies and explodes as a nova or supernova, what it does is it scatters all those heavy elements that it has fused together throughout the rest of the universe, which is how we end up with all sorts of heavier elements. So in other words, when people talk about we're all just made of stardust, it's true. All the different elements that you and I are made of are from stars fusing together hydrogen atoms and then eventually blowing up, scattering that stuff around, and eventually those elements, you know, settle here on Earth and make up us. It's kind of freaky, right? So again, nuclear fusion is this idea of combining together light nuclei to form a heavier nucleus. So here's an example that we have right here. So we've got two different hydrogen isotopes. At the top we have tritium. Okay, and tritium, if you'll notice, it has one proton, which is why it's hydrogen, which is represented by this red dot here, and then two neutrons, which are represented by these white dots here. It's called tritium because, if you note, there are 3 total nucleons in there. It has a mass of 3. Now let's say that this tritium runs into a deuterium, which again is another hydrogen isotope, this time with 2 nucleons, 1 proton, 1 neutron. Now when those two fuse together, first of all, we get energy. But second, those nucleons will rearrange themselves. So one way that they could do that is we could end up with a helium-4 atom with 2 protons and 2 neutrons, and then 1 extra neutron that just kind of floats off by itself. Now if we wanted to write a balanced equation to represent this reaction, first of all, same rules as before. We have to conserve charge and we have to conserve mass. Key ideas in writing these nuclear reactions. We could write it this way. So we've got deuterium here. It's got a mass of 2 and an atomic number of 1, so written the same way as before. And then tritium with a mass of 3, still atomic number of 1, since we're still talking about hydrogen. And then when those come together, we end up with helium, which has a mass of 4, atomic number of 2, a neutron, and then a bunch of energy. So if you note, these reactions very similar to our nuclear decay reactions from before. We're going to use that isotope notation. We're going to make sure that our masses add up to be the same. So if we notice here, 2 plus 3, that's 5. Over on this side, 4 plus 1, that's also 5, so we're good there. So we make sure the masses are equal on both sides. We make sure that the atomic numbers are equal on both sides. So 1 plus 1 for a total of 2, and then 2 plus 0, again for a total of 2. Same idea again. So let's go through a few more examples of this. First example to consider, say we've got 2 deuterium atoms, which again are hydrogen isotopes with a mass of 2. And we know that one of the products of that is going to be a proton. So let me show you what that one might look like. Okay. So again, we've got 2 deuterium atoms, 2 hydrogen 2s. We know one of the products is going to be a proton, and then we have to figure out what this other product is going to be. So let me tell you how I figured that out. So I knew that when I combined my 2 deuteriums, I had a total mass of 4. 2 plus 2 is 4. My proton only has a mass of 1, so in order to end up with a total of 4 on this side, I knew that I had to have a mass of 3 in my remaining particle. Then same idea for the atomic number. I had 1 plus 1 for a total of 2. My hydrogen proton only has an atomic number of 1. To have it add up to 2, my other particle also had to have an atomic number of 1. So what I determined then is that when I had my 2 deuterium atoms come together, if they release a proton, the other thing that they're going to release is tritium. That's the only other possible product, so that we end up with our masses equal on both sides and our atomic numbers equal on both sides. Now, just FYI for funsies, the energy released from this particular fusion reaction is 6.3 times 10 to the negative 13 joules each time this reaction occurs, which is not in and of itself very much, but then when you think about the gigantic mass of our sun and how many of these reactions are happening at a given time, just letting you know the energy output of the sun is 10 to the 34 joules per year. So there's a lot of these reactions happening and adding up all that energy. And just to kind of give you a sense of comparison, a megaton hydrogen bomb releases 4 times 10 to the 15 joules of energy. That's a lot, but way less than the energy output of the sun. Okay, so just to put this in perspective a little bit. Now let's consider another one. For our second reaction, we're going to look at combining deuterium and tritium to produce helium-4. So I want you to pause the video, see if you can figure that out. These are our two reactants. We know one of our products is going to be helium-4, and then we need one other product that's going to make our masses equal on both sides and our atomic numbers equal on both sides. So pause. Okay, at this point, hopefully you've tried writing out that reaction. This one's a little boring because this was the first reaction I showed you. We've got deuterium and tritium making helium and then releasing one extra neutron so that our masses end up being the same on both sides, 5 on both sides, and our atomic numbers are the same on both sides too. Okay. Last example of a fusion reaction that we're going to look at is lithium-6 combining with deuterium, and we know that helium is going to be one of our products. So again, pause the video, see if you can figure this out. Okay, here's our final reaction. Here we've got lithium-6, so we know it has a mass of 6. Lithium always has an atomic number of 3, so there's our lithium. And deuterium is hydrogen with a mass of 2. And then if we determine that helium-4 is one of our products, what we'll find in order to make the masses and atomic numbers equal on both sides is that our other product also has to be a helium-4 atom. So this comes out to be 2 helium-4 atoms that are produced from this particular reaction. So that was fusion, where we were taking 2 smaller nuclei and smashing them together to make something bigger each time. So if you notice, each of these, we had some smaller atoms and we were producing bigger atoms as a result of that. Now we're going to look instead at fission, which is the exact opposite process. So while fusion was putting 2 small things together to make something heavy, nuclear fission is where we take a heavy nucleus and we split it apart into 2 smaller nuclei. And our usual mechanism for doing this is throwing a neutron, basically, at our heavy nucleus. And that's really all there is to it. So if we shoot a neutron at our nucleus with the right speed, at the right location, all the conditions are exactly right, what we can do is get that neutron to stick to that nucleus, making it unstable, and then it basically explodes apart into 2 or more smaller nuclei. So we've got a fission reaction shown right here where we've got uranium-235. We hit it with a neutron, it becomes unstable, and then it spits out these 5 different products along with the 2 times 10 to the 2 kilojoules per mole. That's energy that's also being released as a result of this product, this reaction. So if we were to write this out as a balanced equation, again, we're going to use isotope notation. We're going to make sure the masses add up on both sides, and we're going to make sure that our atomic numbers add up on both sides. So in this situation, our 2 reactants are just our uranium-235 and our neutron. So those are the 2 things on the left side of the equation here. The things that get spat out as a result of that are, we've got our krypton-92, we've got our barium-141, and then we've got 3 of these guys. Now we could either look at them and say, hey look, they look just like the neutrons that we started with, they must be neutrons, or our other option is we could add up these masses and see that the mass over on the right is 3 less than the mass over here on the left, so that these 3 particles must be neutrons to make up for that missing mass. Okay, but again, same exact deal as before. We just put all of the things that come together on the left, all the things that get spat out on the right. We make sure that our masses add up. In this case, both sides, our masses add up to 236. You can check the math on that if you don't believe me. And our atomic numbers add up to 92. Okay. So here we have another fission reaction happening. Again, we've got a neutron that's hitting uranium-235 and makes an unstable nucleus, and we get these 5 products as a result of that. So I want you to go ahead and pause the video. Try to write a balanced fission reaction to describe this. Okay, hopefully you paused and hopefully you wrote this down. So here's the correct reaction to describe this. So we've got, again, uranium-235 plus a neutron, and then we've got strontium-90, xenon-143, these are all shown to you, and then in order to make the masses balance out on both sides, we know that 3 additional neutrons must be spat out as well. Plus there's a bunch of energy that's being released. Now, we can use that famous equation E equals mc squared to figure out how much the mass got changed and therefore how much energy got released. I'm not going to ask you to do this, but just to give you a sense of what's really happening here. From this single fission reaction, we get 2 times 10 to the 13 joules per mole of uranium-235. As a point of comparison, if we were to combust 1 ton of coal, that's only 5 times 10 to the 7 joules. So this is why nuclear energy is really a very energy-dense option. We can get a lot of energy out of these reactions. Okay. Now what you'll also notice is that it seems like each time we have one of these fission reactions where we're shooting a neutron into one of our nuclei, we end up with extra neutrons being shot off again as a result. And this can create this chain reaction, basically, where each time we get fission happening, additional neutrons get spat out of our nucleus, which can then hit other atoms and prompt more fission to occur. And this is why we end up with these very powerful, explosive sorts of reactions from something like an atomic bomb, which is basically just a fission chain reaction. So if we just start with 1 neutron and 1 nucleus and it hits it just right, that's going to release more neutrons, which are going to hit more nuclei, creating more fission, releasing more neutrons, and so forth until we get one heck of a reaction, basically. So again, why we care about these things, where they show up. Fission, when we're taking a large nucleus and splitting it into 2 or more smaller nuclei, that's what's happening in the atomic bomb, first of all. And on a smaller, more controlled scale, that's also the source of energy in nuclear power plants, where we're creating fission reactions. Fusion, on the other hand, is the idea behind the hydrogen bomb, which is different from the atomic bomb. There we've got fusion happening with our little hydrogens getting fused together, and also, the sun and all the other stars out there. So this is where we actually see fusion. Okay. Now, some last little notes just to kind of explain fission and fusion and how they're actually used. So just a little bit of information about nuclear power plants. About 17% of the world's energy comes from nuclear power. That's really headed up mostly in Europe, where they're using a lot of nuclear power. Here in the United States, we're still only getting about 20% of our energy from nuclear power specifically. Now, one thing that tends to concern people a lot about nuclear power plants is the potential for additional exposure to ionizing radiation. And I'm not going to say that those fears are unfounded. I think there's absolutely, legitimacy to that. But at the same time, I want you to consider the relative dosages that we get from nuclear power plants compared to a variety of other sources. So here we see different doses of radiation from various sources each year. What we'll see is that we get a lot of our radiation from, first of all, cosmic rays. There's just radiation bombarding us from the cosmos all the time, just as a result of what we assume is just background radiation that's still going ever since the Big Bang, basically. So we get radiation hitting us all the time anyway. There's radiation coming out of the ground and the surroundings. There's radiation that we absorb from the food that we eat, from the people that we're sitting near. They're emitting radiation as well. And so when we compare all of that radiation to the amount that we get from nuclear waste, for example, Yes, obviously the more radiation that we get exposed to, the worse off we are, but the fact is that as it stands currently, the amount of radiation that we get from nuclear waste or from nuclear power plants is pretty small compared to the amount that we get just from everyday sources like other people, the atmosphere, etc., that we don't really have any control over. So that's just to give you a little bit more insight into where we're getting our exposure to radiation from. That being said, if you get excessive amounts of radiation, if you get lots and lots of x-rays for medical reasons or whatever else, there are some risks to you. First of all, radiation can cause damage to your reproductive cells and reproductive organs, basically by interfering with the cell division and DNA transcription and translation process, where basically at that point the cells are not creating the correct proteins. So that can cause your future children to bear the consequences of your, indiscretions. You can also have somatic damage, which basically means actual direct damage on you as a person, which can include things like burns, cancer, etc., etc. Okay. Now, the extent to which you actually get this damage depends on a few different things. First of all, the type of radiation that you're being exposed to. So again, gamma radiation is going to damage you a whole heck of a lot more than alpha radiation will, just because gamma penetrates tissues so much more thoroughly than alpha radiation can. Secondly, the half-life of that isotope, which basically means how quickly it's decaying and how much radiation it's giving off, and we're going to talk about that in our next and final lesson in this unit, as well as the amount and duration of exposure to whatever that radiation source is. Okay. So again, excessive radiation can cause burning, can cause cancers, can create different mutations. If you watch The Simpsons, you've no doubt seen this little friendly fish. And then more acute radiation sickness can have some slightly more, exciting results, such as hair loss, vomiting blood, all sorts of beautiful, wonderful things. So in short, radiation, not so good for you. But are you getting exposed to some of it anyway? Yes. Is some amount of it going to be fatal to you? Probably not. So anyway, that's just a little basic information on fission. I hope you learned something, and I will see you guys soon.